This is a bit late. Okay, thank you. I've been worrying here away, speaking to myself. I frequently do that because I like speaking to an intelligent person. But, okay, can you hear me now? My word, apologies. Okay, sorry, I hope you can fast forward the recording. Let's go, let's go. Let's restart. Let's restart. Let's restart. What I wanted to say, and you needed some audio for this, is the fact that the rate increases, goes through a maximum, and then decreases again, up till a point where it reaches zero. And this zero doesn't correspond to an x, a conversion value, where x is equal to 1. This is x is equal to 1. This is at 0.8 to 0.81. Few things that you should be able to deduce from this figure. First one is it's an exothermic reaction. Why? If it was an endothermic reaction and I gave you the corresponding rate graph, it would start at the initial rate and there will just be a decrease in the rate until it went to equilibrium. So here, where Arrhenius works for the forward reaction and that increase in temperature, remember it's adiabatic. So there must be an increase in temperature that results in this increase in the rate to a maximum value at x is about 0.54. So this is what you needed to see. It's exothermic and it's equilibrium limited because the rate goes to 0 at 0.8. For question A and question B, this is me testing your resolve. I can be mean sometimes and ask questions that is meant to confuse you if you are not sure of your facts. And I ask for the CSTR maximum conversion and the PFR maximum conversion. And what you have to realize is that this will be the same for an adiabatic reactor. The theory that I wanted you to consider here is this X equilibrium line and my adiabatic energy balance. Regardless of whether I have a CSTR or a plug flow reactor, this thou shalt not pass point over here, which in the case of this reaction is at 80% or 81%, is the same regardless of whether you had a CSTR or a PFR. And I wanted you to write down 0.81 or 81% or 80% and 81% for both. It tests your resolve. The type of reactor does not, when I have an adiabatic, I can for any reaction ask you what is the maximum adiabatic conversion without specifying the reactor type. Right, questions on this? Cool. So now another important aspect of the stat is whether you understand that if I ask you to draw an X versus volume graph for a PFR, I am asking you, do you know that the XdV is directly proportional to the rate? Because I could derive in my mole balance that FA naught dx dV is min Ra. And therefore this slope, the change in the slope, delta, small little delta x over delta V, I want to see in this figure must correspond to whatever you observed in that one. And now the errors that I spotted in the graphs that was published in the Slack, thank you very much for participating, is that many students, so it starts at 0, then there's an increase in the rate. And the increase in the rate means that there's an increase in the slope. So the slope may start off low, but then it's increasing. There's an increase in the slope of delta x, delta V, up to the point where x is at a maximum. Now I'm over-exaggerating there. Some of your graphs look better. And what I wanted to see in this test is that people realize that this is at about 0.54 because it corresponds to that maximum point. Then the slope is going to start to decrease. So I will see this flattening out of that curve. However, it does not go to 0. That is not there. It stops at 70%. So please scratch out on your figure, scratch this out. I wanted the actual conversion in the actual PFR figure, which yes, it would have. If I made that PFR really big, would have finally achieved the point where the rate goes to 0, and therefore the slope of this line must also be 0. So there's the 0 slope, but I am not there at the point where I have my 70% conversion. So you weren't expected to give the volume. In my answers that I publish, you will see that I give volume values, but that's because when I set up the question, I used actual data. So I have more information than you in order to give the volume. I wanted to see that you could see that inflection point at 54%, mark that, and that it stops at 0.7 with an increase in the rate initially, maximum decrease in the rate after that inflection point. Questions on that? Non-additive affect the maximum, definitely. So Winfrey also, we are going to explore the non-adiabatic reversible reactions in a plug flow reactor after the semester test. So for a CSTR reactor, I can ask you, because I can change my slope. We will discuss that in that 4.2 Winfrey, but definitely it will change that maximum point. Absolutely, then I can't compare a PFR reactor with a CSTR reactor anymore. Right, so more questions? Cool, so let's just go to the next one then. So this is this that I wanted you to answer, and then I wanted you to size. Now I'm out of space, I'm going to have to redraw everything again. So when you want to make real money, please go and work for Blackboard and change their eraser so that it doesn't erase everything that you've written previously. So you've got the rate. So at any x, you can go and read off the rate value. Right, and I give you a 50% conversion, so you can go and read off that rate. There you go. You can go and read off the rate, and therefore you can quite easily solve the volume just from the mole balance, because you know FA naught, you know your FA, because that is FA naught 1 minus the given conversion, and that's plus the RA times V. And you know what your rate is, so you can go and read that, and that will be the only unknown in your mole balance. So you should easily be able to find that volume. Remember, once again, definitely some scope for a plus minus value around the given answer, because we read this off from a figure. So please don't expect to get point on exactly my answer. But then I asked you to also find the temperature of that reactor. So you had no information on del H of the reaction, you had no information on CP value. So in order to solve that, you had to realize that for my, because del CP of the reaction is 0, I will get this linear energy balance, where I can say temperature is equal to temperature naught minus epsilon times del H reaction. And that will be true regardless of whether I have, divided by, of course, everything that comes in. And that will be the same whether I have a CSTR or a plug flow reactor. This is the equation that will result. In this case, my epsilon value is going to be FA naught times X. And this is FA naught times the CP of A. So the two FA values will cancel out. And in the end, this equation, so apologies for now going to 0, and let's go for some open white space there, right? So if I have my final equation, it looks like this. T naught, and then I have min del H reaction divided by CPA times X. This is known, you know your inlet value, so this is the 70% value, and I gave you the outlet temperature of that plug flow reactor. This as a group, you cannot solve them separately, you don't have enough information for that, but I could solve them as a group of terms. So you would be able to find that this slope is about 253 in the unit system that is given. So just for a hint, you can solve that. And then for my CSTR, I use exactly the same equation for the CSTR, but now my X is that 50%, the T naught is the same, that was the same for both, and I can solve for that temperature. So that is as far as that 4.1 goes. Right. Any more questions on 4.1? Going. Right. Anybody that wants to raise a concern regarding that 4.2 before we go back to our sessions? Maybe I can just say that last question where I ask you to size the plug flow reactor is me being seriously mean again. It is me being seriously mean and testing your resolve. Right, so that's just a hint. Size a plug flow, an adiabatic plug flow reactor to achieve 70% conversion. That's me being mean and testing your resolve. And then remember, if we want to minimize volume, we want to maximize the rate. And in the second reactor, you have no choice. The concentration is given. You can find the concentration because you have a given conversion based on your inlet molar flow rate. FA naught, you know what the molar flow rate is, you know what your volumetric flow rate is, so you know the concentration in your rate equation. That is fixed in your rate expression. So you've got K CA minus K over KC CB. Those two variables you've got no design decisions over in your second reactor. So you have two reactors in series, and that second reactor, you must operate at a specific concentration that corresponds to a 70% overall conversion over your reacting systems. And so therefore that is fixed. The only thing you can vary is the temperature. So what do you need to change in order to find where the rate is at a maximum for this specific concentration? That's the hint for this reactor. The first reactor is operated adiabatically, so consult the Levenspiel plot discussions on your slides. And then some other points that I want to share is if you want to plot the multiplicity plots. So multiplicity plots means I want to, let me just refer you to your TAT 2.1. I want to construct the mole balance versus the energy balance. And for your mole balance, you've got now this equation for the rate. So it becomes very non-linear in temperature. So my suggestion is when you want to construct your mole balance, choose a T range of values and rather solve for X from your mole balance for that CSTR. So remember your CSTR will FA naught minus FA naught 1 minus X plus RA times V, and in this RA it will also be a function of X and temperature. Your volume will then be specified for your different reactors. So what my suggestion is, choose a reasonable range of temperature values and solve X from your mole balance instead of choosing a lin space of X values to solve the temperature from the mole balance when you want to construct your mole balance figure. Then you can actually get an algebraic, easy to solve expression if you want to test for multiplicity. Right, so I'll hang around for a bit and I'm going to stop the recording now. So please return to your Slack groups, continue working on that 4.2.